Swayam Prabha. Digital India. Educated India.
So welcome to lecture 7 of the Statistical Thermodynamics for Engineers. So just a brief recap. Okay, if you recall what we did in the last lecture is that W is greater than W most probable greater than W bar, where W was the total number of microstates. These are the total number of microstates in the system, and this is the mean number of microstates. Okay, so this was already there. Now, if your n is 10 to the power of 23 and m is equal to 2, okay, so W, that is the total number of microstates, is given as m to the power of n, which is basically 2 to the power of n. Then W bar, the mean number of microstates, is basically 2 to the power of n divided by n plus 1. Okay. Now, if we now look at it carefully, ln W, that is, if we take the natural log of W, it will be n ln 2, which roughly translates to about 7.0 into 10 to the power of 22. Okay. ln W bar, which is basically the logarithm of the mean number of microstates, ln W2 minus ln n plus 1, which also translates to 7.0 into 10 to the power of 22 minus 53. So what we can see here is ln W bar is almost the same as ln W, right? Because you can see that this particular number is so large compared to this that these two are basically one and the same. So in other words, this also means that ln W is therefore almost equal to ln most probable, which is almost equal to ln W bar. So all it means is that the logarithmic of the total number of microstates is almost the same as the most probable number of the number of microstates associated with the most probable macrostate, and that is almost equal to the mean number of microstates. Okay, so that is illuminating. So what we can say is that in the limit where n approaches infinity, ln of Wmp divided by ln W is almost equal to 1. Or in other words, it seems that for macroscopic thermodynamic systems, almost all microstates are associated with the most probable macrostate. So this is the most important inference, that because this is true, and because n is pretty large, it seems that for macroscopic thermodynamic systems, okay, almost all microstates, this is the most important part, almost all microstates are associated with the most probable macrostate. All microstates are associated with the most probable macrostate. So the most probable distribution must represent the equilibrium particle distribution. So this therefore represents the equilibrium particle distribution. Right. So this represents the equilibrium particle distribution. Okay, so that is pretty illuminating to begin with. Okay, so let us now look at the first level of statistics. Okay, because we have now covered the different aspects of macrostate, microstate, we know a lot. We know distinguishable, indistinguishable particles also. So we are going to look at Bose, Einstein and Fermi Dirac statistics. Bose, Einstein and Fermi Dirac statistics. Okay. So first let us look at the Bose, Einstein or the BE statistics. Okay. So the BE statistics, that is the Bose-Einstein statistics after S.N. Bose and Albert Einstein. So the premise is that indistinguishable particles with no limit on the number of particles okay, per energy state. Okay. So let us consider, we will do it slowly, one energy level. Okay, and let us consider the number of ways, okay, in which NJ bosons, which is the number of particles a single energy level, bosons in a single energy level EJ, okay, EJ may be distributed in GJ energy states. So we consider one energy level and we are going to see the number of ways in which NJ bosons, okay, because Bose-Einstein statistics are their bosons. So these are the number of bosons in a single energy level EJ may be distributed in GJ energy states, where GJ is the degeneracy. Okay, so you have basically GJ compartments. You have NJ indistinguishable particles. There is no limit on the number of particles per energy state. So one energy state can have as many number of particles as you want. So we have to consider that how this distribution is possible. Okay, so this is the problem is therefore equivalent to NJ, identical, indistinguishable objects. We already have done this. Objects can be arranged in GJ containers. So it is like what we knew as M containers. So it's like GJ containers with no limit. Okay, in the number of objects per container. Got it? Per container. So therefore we write it as Wj is equal to Nj plus Gj minus 1 factorial divided by Nj factorial Gj minus 1 factorial. Okay, so these are the number of arrangements that we have. Okay, so since each energy level is independent, so now since each energy level is independent, right? Because it does not depend on the other one. Each energy level is independent. So this is important. Independent. Okay. So the total number of ways of obtaining an arbitrary particle distribution. Arbitrary particle distribution is, if we write it as BE, as Bose Einstein, is basically will be the multiplicative of all the J energy levels into Wj, which essentially translates to J Nj plus Gj minus 1 factorial divided by Nj factorial Gj minus 1 factorial. Okay? So this is essentially what the distribution should look like. So WBE is basically the generic number of microstates, right, per macrostate for B statistics, right? B statistics. This is the generic number of microstates per macrostate, for the Bose-Einstein statistics. So you got the point. So these are indistinguishable particles. Okay, they are identical, and how they can be distributed in Gj containers. There is Nj number of particles in energy level. So what you do after this, we follow the protocol. That means we take the logarithm of WBE, which therefore converts this multiplicative sign into an additive sign. Okay, so this becomes ln Nj plus Gj factorial. Okay, so these are all within bracket, by the way. So ln Nj factorial minus ln Gj factorial. Okay, so Gj is much greater than 1 because we said that degeneracy is usually a large number. Degeneracy is usually large number to begin with. Okay, so use the Stirling's approximation. Okay, so which is basically ln n factorial is equal to n ln n minus n. Okay, so this is Stirling's approximation. When you apply it to this particular context, it's ln WBE is equal to summation J Nj plus Gj ln Nj plus Gj minus Nj ln Nj minus Gj ln Gj. Right? Okay, now simplifying it a little bit further. So this gives you J Nj ln Gj plus Nj by Nj plus Gj ln Gj plus Nj Gj. Okay, so this will be your Bose-Einstein statistics, right? So this up to this particular point we have worked out the Bose-Einstein statistics, because this is what the statistics would look like, but we are not done yet. So we will do the Fermi-Dirac now, take it up to the same level, and then we will see the most probable distributions. Okay, so the Fermi-Dirac statistics. So next one is the Fermi-Dirac statistics. So these are valid for fermions. It's called fermions. It's a class of particles. So again, the same thing, Nj fermions in Ej energy level, right? In Gj containers. But this time we have a limit with the limit of one particle per container. Okay, particle per container, and they are of course identical and indistinguishable. All right, so Wj is equal to Gj factorial by Nj factorial into Gj minus Nj factorial. This we already know. This accounts for this. This accounts for the indistinguishability. Accounts for it. This we already know as well. Okay. So the Fermi-Dirac statistics therefore boils down to again the multiplicative of all Wj's, which essentially translates to this Gj factorial divided by Nj factorial Gj minus Nj factorial. Okay. So this is once again the generic number of microstates per microstate. Also the same assumption valid because the energy levels, this essentially translates to that the energy levels are independent. Energy levels are independent. Okay? So energy levels are independent. Okay? So now, if you now cast ln w and d, okay, once again we take the log, it's j ln gj factorial minus ln nj factorial minus ln gj minus nj factorial. So this is what it is. Again, use the Stirling's approximation. Which essentially translates to WFD is equal to summation j nj ln gj minus nj divided by nj minus gj ln gj minus nj by gj. Okay. So this will be Fermi-Dirac statistics. So you saw how we used the statistical tools that we developed for very generic situations and how it is applicable when you actually do the Bose-Einstein and the Fermi-Dirac statistics. Right? Okay. So now we choose the most probable distribution. And that is what you want to find out. So this is ln w, whether it is Bose-Einstein or Fermi-Dirac, doesn't really matter. It's like the distributions are like this. This is nj ln. It depends on which distribution you are looking at. It looks something like this: plus minus gj ln gj plus minus nj by gj. Okay, so this is the distribution that you are looking at. So the most probable distribution, in order to find that out, our task is to find out the most probable distribution, right? So these are the Fermi Dirac statistics for any arbitrary distribution, right? Distribution. So for that, we introduce two constraints in the system, right? First one is that summation of nj is equal to n, okay, which is basically mass conservation. And then you sum over nj ej is equal to e, which is basically the energy conservation. So these are both common sense, right? Okay. So we saw that, okay, now if we write once again ln w is summation j nj ln gj plus minus nj minus nj ln nj plus minus gj ln gj plus minus nj minus plus gj ln gj. So this is the total expression. What you do is that you differentiate first, because you have to find out the most probable distribution. So once you do that, okay, you get ln. So I'm writing it a little smaller just so that you can see it properly. Gj plus minus nj divided by gj plus nj minus ln nj minus 1 plus gj plus minus nj tnj. Okay, so that is what we have done now. Okay, so if you now do a little further, then gj plus minus nj, work out the steps. So these are the things that you get. Now, gj and ej are taken constants during the differentiation. So we have taken gj and nj, okay, gj and ej, sorry. So ej are taken as constants during differentiation. Okay. So gj is an integer, because it's degeneracy, and ej is, of course, it's basically a function of the total volume of the system. And it is constant. It's constant for an isolated system. It's constant for an isolated system. So therefore, summation dnj is equal to 0. Okay. And summation j dnj is also equal to 0. Okay. So now we have the situation, and so introducing the concept of Lagrange multipliers now. So introduce Lagrange multipliers. Okay, what you have is therefore j ln gj plus minus nj minus ln nj minus alpha minus beta ej into dnj is equal to 0. Alpha, gamma, beta are the Lagrange multipliers. Now, this particular thing can only be achieved. This can be achieved. For all j, if and only if, that's why I write if gj plus minus nj divided by nj is equal to alpha plus beta g. Okay, so therefore nj is equal to gj divided by exponential alpha plus beta ej minus plus 1. Okay, so this will be the most probable distribution, and as we saw, it is only distribution, and for large n it is, and for large n it is only distribution. Okay, all right. So as you can see now, right? So this is, depending on which one you are looking at, this is the Bose, Einstein, and the Fermi, Dirac, the most probable distribution. This is how nj particles are distributed in gj energy energy states. Okay, so this is a rather interesting thing, and just to recap, alpha and beta are called the Lagrange multipliers. Okay, this is valid, as you can see, y. Okay, and ej is basically the function of the total volume of the system. It is constant for an isolated system, if you recall. Okay, and that comes from your macroscopic definition, and we have done a lot of stuff using Stirling's approximation and stuff like that to arrive at this particular expression. So the next class we are going to look at, or in the next lecture, we are going to look at entropy and the equilibrium particle distribution. So coming up is entropy and equilibrium particle distribution. So this is what is coming up next in the next lecture, which will be lecture 8, and there we are going to look at that how the most probable distribution can be found out. But here in this case you can see, because we do not know alpha or beta, these are unknowns, right? So therefore this distribution, that whatever I have given you, is incomplete. This is incomplete since alpha and beta are unknown. So hence you cannot really have a fair idea of what is your nj going to be. So nj, if it is the most probable distribution, you still need to see what is this alpha and beta all about, because only then you can find out the most probable distribution, and for that we need entropy and we need a few other things which we are going to cover in the next lecture. So thank you.